Hey, for calculus today, we're going to look at adding vectors graphically. So our learning target is just that. We'll be able to add vectors graphically. So before we do that, I thought, hey, you know what is more fun than watching random stuff from YouTube, right? So here is, I'm going to show you a little clip from YouTube and three questions to keep in mind. What direction is the plane pointing? What direction is it going? Why the difference? Okay. Well, there's more where that came from. You can type in that link down there if you want to watch the whole thing. I'll put the link in Canvas. All right. What direction is the plane pointing? Well, it's like that way. What direction is it going? Straight ahead. Why the difference? I'll let you think about that one for a minute. You probably know the answer already, but we'll come back to that right after this. So we talked about adding vectors yesterday. This very first part we've seen already up here. So we're going to add two vectors. We've got vector u and vector v, a given component form. So u1 is a number and u1 is a u2 is a number, v1 and v2 both numbers. It mentions about a scalar. We're not going to use a scalar right now. We'll get there later. So you just take the two x components, add them together, take the two y components, add those to each other, and there's your new vector, right? So that's vector addition. And from component form, it's super simple, right? It's just adding. But we need to also be able to add graphically. So there are two different approaches we're going to look at for adding vectors graphically. The first is tip to tail. So this is like what we saw yesterday with the confused student who left home and went for a walk around the neighborhood. So if the origin of the graph is like home and you walk off in this direction and then you stop, you turn and you go in a different direction, right? You just, where one vector ends at that arrowhead, that's where you begin the next one, right? So the tip of one vector, that's where you start the tail of the next. The textbook calls it tail to head. I grew up calling it tip to tail, the same difference. So the resultant vector, that's the answer. The resultant vector goes from the origin to the end of the second vector, right? That's like where the pigeon flies, leaving from home and going to where the kid is at, right? You don't draw one vector and then like return home and draw a second vector. That, like, there's no magical teleportation where you start over at home, walk in a different direction now, right? You got to pick up where you left off. So with numerical example here, I've got two vectors. U is 2, 4. I've got that pre-graphed, and V is 7, 3, and I have that pre-graphed also. I'm just going to pull those down onto my graph. So here's U going over 2 and up 4, and then from the end of that, I'm going to draw a vector U, blam, right there, and if I get them lined up perfectly, it'll be pretty close. Okay, so then the resultant is going to be from the origin at 0, 0 to the end of that second vector. And I always color my resultants red because alliteration makes it easy to remember. All right, so this is my resultant. And if we do some quick mental math, the component form of the resultant based on components should be 2 plus 7 is 9. And the y's 4 plus 3 would be 7. And that is actually what we see on this graph. The red resultant vector has gone across 9 spaces and up 7 spaces. I'm drawing a tiny bit off there. That looks better. Okay. Yeah, so there's tip to tail or tail to head. The second approach for graphing vectors is using what's called the parallelogram method. Let me pull some of these. I can use the same two example vectors. Let me just pull these down here so that I can see them for later. And stock of vectors to use. Okay, so a parallelogram method, both of the two vectors you're adding are going to start from the origin. So I've got vector u going off in whatever direction u goes off, and then also from the origin, here's vector v. But in order to complete the parallelogram, I'm going to need extra copies of both of those two vectors to complete the opposite sides of the parallelogram. Okay, so I'm going to do vector u, and I'm going to do vector v also from the origin. And I can say, all right, here are the first two sides of my parallelogram. I need two parallel congruent sides to be opposites. So from the end of the blue u vector, I'm going to put a copy of vector v. And from the end of the first v, I'm going to put another copy of vector u. The resultant is going to go from the origin diagonal across the parallelogram. Okay. Sometimes people get confused, and people get confused, do all kinds of things. But they'll draw a diagonal across the parallelogram from not from the origin, using these opposite corners here, and we don't want to use those. Don't show up for any reason. We never, ever, ever in any method do we use these other two corners. If you can see what I'm pointing with the cursor. Right, so the resultant will always start at the origin, no matter what method of graphing you are using. If we use tail to head, the resultant vector starts at the origin. If we use the parallelogram method, the resultant vector starts from the origin, always. Okay, so you remember a long time ago, we were looking at that YouTube video I showed you with the airplane that was like pointing over here, but it was going over here. And why was the difference? Was wind. In fact, if we'd watched a different section of the video, it actually tells us about the wind. I zoomed in on this. It tells us exactly what direction the wind is blowing. That's the direction, and how hard it's blowing. So there's the magnitude. It's um, airplane pilots are kind of like people in the Navy. They use these weird measurements like knots. I don't know what a knot is. But that is the two things we need to describe a vector, right? We've got direction and we've got magnitude. Okay, so I want to use this airplane as an example of vector addition. So we've got a picture of the airplane approaching that runway as the top view, and it's pointed off to the side because there's a crosswind here, right? So actually the YouTube search I did was crosswind landing. So the wind is blowing straight in from the side. So starting from the red dot, draw an arrow for the plane's direction. We're also going to draw an arrow starting from the red dot, showing the direction that the airplane is pointed in. All right, it's pointing off this direction, just like in the video, it's pointed off to the side. Right, and then the wind coming straight in from the side, perpendicular to the runway, and then we're going to add those two things together. Right, so let's see. I got some wind is going to go this direction, or sorry, airplane is going to go this direction. We'll do the airplane first. We'll do the airplane in green because everybody likes a green airplane. And then if we went straight sideways, they got the wind, and wind comes from those dark storm clouds that are blue. So we got the blue wind coming straight into the side, and then if we add those two together graphically, we got the airplane going off to the diagonal. I got the wind perpendicular to the runway to blow the airplane back onto course. As we watch those airplanes, they're pointed sideways, but they're moving straight down the runway. The resultant is going to go straight up the runway. I started off to the side a little bit. Let's get that fixed. There we go. And resultants, always in red, always in red. Okay, so I pre-drew this just so it'll look nice. So we got the airplane's engines pointing in one direction, the wind blowing it sideways. This only works if we're using vector addition. Otherwise, you know, the one vector and the other vector, that I don't know, if we're not doing vector addition, if we're trying to think about this some other way, it's not going to work. But fortunately, we're doing vector addition and it all works out. So you point off into the wind blows you back onto course, and you actually the path of the airplane is straight up the runway. Let's do a couple of more examples. How do we graph scalar multiplication? We looked at scalar multiplication yesterday, so we're going to look at a couple of different vector operations. Sketch and find the component form of 3u. All right, well, the components of u are up here. I got 2 and 4 as the components. So if I'm going to graph that scalar multiplication, I need to graph vector u 3 times. So there's one u, and then I just stack them tip to tail. It's like vector addition, right? And there's 2 u's, and then I don't want to overlapping, then it won't work out right. There's 3 u's. Um, and so by the time, if I keep these things actually lined up properly, try to get this one moved back a little bit. It's, come on. Ugh. There we go. That's better. All right. So the resultant vector is still just 3u, but when I stack those 3 individual u's together, I've gone from 0 over here to 6, 12, right? And if we're multiplying these components by 3, 3 times 2, 2 times 3 is 6, and 4 times 3 is 12, right? So that probably is not much of a surprise. Okay, but that's how we graph scalar multiplication. All right, let's look at another example. It's down here. So I'm going to start with those same 2 vectors. Here's u, here's v. This time we're going to do 3u plus v. I should have saved what 3u looked like. So to graph this, I'm going to do 3 u's again. There's 1u, there's 2u, and finally here's 3 u's. From the end of that third u, I'm going to put vector v, right? So from the end of that last blue arrow, right there, and then I can draw a resultant starting from the origin at 0, 0, going to the end of where that green arrow just ended. Get this lined up right so that the arrowhead's at the right place. I'm going to change colors because resultants are always in red. Always in red. Okay, so if I want to work this out in component form, I'm going to do this in a couple of pieces. First, I'm going to take vector u, and I'm going to multiply it times 3. We just did that a minute ago. It was not even a minute ago. So 2 times 3 is 6, 4 times 3 is 12. That, whoa, is 3u. Okay, I would label it on the left, but when I tried to write over there, it did weird things with my computer screen. So we'll just leave it there. And then I'm going to add that. I'm going to stack these up vertically so I can add straight up and down my columns, comma, plus. Okay, so when I add this, I should get the component form that will match what I just drew in the graph over here, right? 6 and negative 7 is going to make negative 1, 12 and negative 3, that's 9. So my result, negative 1, 9. And I didn't label this one, that one was V. Okay, so look, if I look at the graph, this red resultant vector I just graphed goes left 1 space and up 9, negative 1, 9. Blam, just like that. Awesome. So we've seen scalar multiplication, we've seen vector addition. One last thing we got to look at right now, and that is how do we do subtraction? Okay, subtracting a vector, if we have components, is no big deal. You just subtract, right? But for graphing purposes, you can't graph subtraction. How do you take a vector away from something you already drew? That is weird, right? So in order to do subtraction of vectors on a graph, we're going to have to change the problem up a little bit. So if we started with a subtraction problem, negative 2u minus v, we're going to have to rewrite this subtraction as adding a negative, right? And that's not the way the problem was originally written, but it's mathematically equivalent, right? Those are the properties of equality say so adding a negative is the same thing as subtraction. So I'm just going to insert this scalar multiplication of negative 1 onto the v. So I'll have negative 2u plus negative 1 times v. And so I'll have to do that scalar multiplication just by a negative sign before I do the graphing. Okay, and if you don't need to graph, you wouldn't do this. But for graphing purposes, we can only add vectors on a graph. We can't subtract. So if I was going to do, as an example, negative 2u minus v, I'm going to have to, first of all, rewrite that as negative 2u plus negative 1v, right? So let's take the negative 2u part first. This is going to be in blue, so I'm going to multiply both components by negative 2. So negative 2u, the vector, is going to be negative 4 and negative 8. And then I need to take vector v and multiply it by negative 1. So this is going to be the vector negative v. So multiply both by negative 1. That's just going to change the sign. So I'll have positive 7 and positive 3. There's my comma. Oh, stop doing that. Plus. And then change to red so I can get my resultant. So I'm going to add straight down these columns. Negative 4 plus 3. What? Negative 4 plus 7, which is 3. Got ahead of myself. And negative 8 plus 3, that's negative 5. I don't think I have enough room to write the whole word. Resultant. Squeeze it in there. Okay, so let's see what that looks like on the graph. So I need negative 2u. All right, well, if I'm going to do negative 2u, that means this is pointing the wrong direction. So I am going to flip this thing around so it points in the exact opposite direction. So you can see it's like starting at the wrong place, but ending at the origin. So it's going backwards. It's going negative 2 and negative 4, but I actually want to point the other direction. There it is. So it's gone negative u. That's once. And I need to do that again. So just grab a copy of that. Blam. Okay. And then from the end of, I know they look like ends now, but that's just because my user are upside down. From the end of that last blue vector, I'm going to add on to it the opposite of vector v. And so vector v, this one is pointing the wrong direction. I'm going to have to flip this one around also. Okay, so if I put that right there at the end of the blue vector, that's like moving to the right by 7 and up 3, just the same thing we got in our component form over here. And now the resultant, whoops, that's too far, goes right there. And we're going to change that to red so it matches our color scheme. And if we check what I have on the graph right now, this red vector goes 3 spaces to the right, down 5 spaces, so 3 and negative 5. Okay, the result, the component form was really not, I think, what we had a question about, but how to graph things. So when we're graphing negative vectors, if you have a negative scalar multiplication, we're going to have to flip it around to make it go the exact opposite direction it would have gone otherwise. That's what the negative sign means. It's like a reverse. And for subtracting, we're going to change that subtraction in the original problem into adding a negative number. All right, well, I think that should prepare you. Good luck, and watch out for those crosswinds.